A very good morning to everyone present here. I am Suriyah Dhinakaran. I am a researcher at the Institute of Earth Observation, EURAC Research, Bolzano, Italy. In today's session, we'll guide you through two Jupyter notebooks. So to get started, head over to the zarr.eopf.copernicus.eu website. So once you're in the landing page, click on the Resources tab on the top of the page. On the left-hand side, you'll see an index. Select the Jupyter notebooks from that list. Scroll down slightly and you should see two options with find out more. Click on any of those. This is the web rendered Jupyter notebooks. To access the compute environment, we'll be using a Jupyter Hub instance developed by EODC. Here's how to launch it. Click the rocket icon at the top right corner. A URL tab will pop up asking you to enter a URL. Type in binderhub.user.eopf.eodc.eu. Sign in using your CDSC account. So once you're logged in, the Binder Hub will lead you to a Jupyter Hub instance. It'll take a moment to load. You're all set now. In case you don't find the GitHub repository pre-cloned within the Jupyter instance, we can do it ourselves. If you have the terminal access here, it's git clone. Please use this GitHub URL. So once the cloning is done, you are all set now. You can find the tutorial notebooks in the following directory, that is within EOPF sample notebooks, within notebooks, and within the Sentinel-2 folder, you'll find the two notebooks that are used in this tutorial. We'll first start with the safe versus Zarr metadata comparison. In this tutorial, we'll begin by exploring the most efficient techniques in metadata extraction between the legacy safe format and the EOPF Zarr format using GDAL and Xarray with a sample Sentinel-2 L2A dataset. In the coming weeks in this webinar series, we will also introduce the use of Snap in doing this exercise. We will also highlight how Xarray can be used to extract metadata, emphasizing the differences between what is present in the safe format but absent in the Zarr format. The Zarr format stores attributes differently to the safe format, and therefore it's not straightforward to get some specific fields from them. We'll start by importing the necessary libraries, that is GDAL and Xarray. First, we'll start with the metadata extraction of safe format using GDAL. The source file is a zip file hosted on an S3 object storage, and we can get the information we need by pointing to the specific .xml metadata file. Since the intention is to find the differences in extracting metadata, let's point the .xml metadata file within the safe format, thereby avoiding the download of full safe.zip data. As you can see here, we use VSI zip, which is GDAL's virtual file system driver for reading zip files without extracting them. We also use VSI curl, which is also a GDAL's virtual file system for accessing files over the HTTP protocol, followed by which we have the URL of the object in the object storage pointing towards the .xml file. We use open method from GDAL's dataset class to open the .xml file. Then we use get metadata method of GDAL's dataset class to extract the metadata. The key metadata of interest are general metadata that includes mission ID, product type, etc., and acquisition and geolocation metadata, and also the radiometric and atmospheric metadata. Here we use .get method of Python's built-in dictionary class to extract the metadata information and reprint it here. The quantification values and radiometric offset values are important to extract the bottom of atmosphere values, aerosol optical thickness, and scene average water vapor. These values helps in converting from DN values to the reflectance values. However, using GDAL, the offset values for each bands are not accessible, which is crucial for the calculation of reflectance values from the DN values. We can also extract the sub datasets using the get sub datasets method of GDAL's dataset class, which provides a hint about the product structure where different bands are available at different resolution. For example, you can find the description of each sub dataset. This sub dataset contains bands B2, B3, B4, B8, aerosol optical thickness, water vapor with 10-meter resolution, and also coordinate reference system. We'll now see how to extract the metadata of Zarr using GDAL. The source file is now a Zarr file, which is the result of original safe product converted using the EOPF library. The file is stored remotely and accessed via GDAL's vSycle driver. The Zarr keyword here tells GDAL to treat the file as a Zarr dataset. The OpenX method of GDAL's dataset class is used instead of GDAL.open. Off multidimensional raster flag ensures GDAL interprets it as a multidimensional dataset. We use the getRootGroup method to retrieve the root group. Here, the dataset is structured into groups. The root group acts as a main container for dataset. And we use getAttributes method for the root group object, which retrieves all metadata attributes. Finally, it returns two nested dictionaries, that is other metadata and stack discovery. With respect to all the general metadata, acquisition and geolocation metadata, the data is organized in a nested dictionary structure, simpler than in the safe format. However, the radiometric and atmospheric data is not available in the Zarr format. Meanwhile, the extraction of the spectral bands along with the central wavelength and spatial resolution is also a bit complicated here. This is done by first extracting the spectral and band information and then formatting the resolution mapping and looping through bands and printing information. We finally access the metadata using Xarray package which support opening Zarr products and can also be used to process the data easily. Here we use the xarray.open data tree, which is a function in Xarray that is used to open a Zarr dataset as a data tree. The engine Zarr specifies that the engine used to read dataset is Zarr. Here the mention of chunks, which is an optional argument, is left empty, meaning that the data is read how it's previously chunked and stored. While accessing Zarr metadata using Xarray, the accessibility to the metadata is even simpler as the attributes exploited by just using the ATTRS method. More straightforward than using GDAL, although the attributes are accessed in similar ways. Now it's time to check out the Sentinel-2 L1C MSI Zarr product notebook. In this notebook, we'll explore how to open, visualize, and plot the Sentinel-2 L1C Zarr product. This notebook will help us in answering the following questions. That is, how do we access the Sentinel-2 L1C EOPF Zarr format? How do we plot the tile location on the map? How do we plot the RGB image of the selected scene? And how do we compute radiances from the reflectance values? And the primary objectives of this notebook is to be able to open a Sentinel-2 L1C EOPF Zarr product from an object storage and also to understand the product structure and how to get specific bands. First, we'll start with importing the necessary modules. We'll import EOPF, we'll import Cartopy and Matplotlib for plotting, and we import Xarray and NumPy for reading and scientific analysis. As we saw in the previous notebook, we use similar method in reading the Zarr product. So again, we now using the Xarray's open data tree function to open the Zarr dataset as a data tree. Let's briefly explore the data tree object. As you can see, there are three primary groups within the data tree object. The first group is conditions, the second group is measurements, the third group is quality. We'll be more interested in the group measurements. We'll explore it in deep. So within the measurements, we have one subgroup. The name of the subgroup is reflectance, and within the subgroup, we have three different subgroups. That is reflectance at 10-meter resolution, reflectance at 20-meter resolution, and reflectance 60-meter resolution, each having unique set of bands. We'll also be interested with the conditions group, within which we have three subgroups. Within this group, we'll be interested with the geometry group. We'll now try to do a simple plotting, that is by accessing the band 1 of the reflectance at 60 meters resolution. This is one way of plotting it, that is accessing the reflectance data stored at 60-meter resolution inside the dataset data tree. We also have an alternative rotation where we can use the dot operator to extract the band 1 data variable. The original data that is in safe format, the data is stored in the unsigned integer 16, that is as dn values, with where the scale and offset values have to be applied. But in case of Zarr, it already contains reflectance values, which means that the scale and offset are already pre-applied to the data. Here in the encoder, you can find the scale factor and offset values pre-applied. The band statistics can be extracted by computing them, which requires download of data. The RGB image can be plotted at a lower scale, that is in a downsample version, or at a lower resolution, or it's also called as decimated version, thus effectively speeding up the process. For meaningful visualization, rescaling and clipping is also performed in the band values. Now we'll explore the product's geolocation. The Zarr product metadata contains information about the product geolocation. We can explore in different ways. So first we'll start with creating an interactive map for which we can now import GeoPandas, and then we'll create a geodata frame using the metadata that is extracted from the Zarr. So we create a feature now from the metadata of Zarr, that is we extract the geometry, and then we also extract the properties. And we also explicitly mention here the CRS that is needed. We provide the EPSG as 4326. We use the explore method of GeoPandas where we can see the feature that is created and embedded over a leaflet map, hovering over which we can see the properties. Yeah. Now we'll try to create a non-interactive map that is plotting the centroid in a global and at a global context. So we primarily use Cartopy methods here. Now we see how to compute the radiances. We see that there's a formula here, that is reflectance multiplied by the sun zenith angle, and we need the solar irradiance value, and we need the U constant that is used in the radiometric correction. Extract the U constant from the metadata itself. And then for the sun zenith angle, we will need to process it slightly a bit different because the sun angle that is stored in the geometry is stored at 5 kilometer resolution. So that's why we have just only 23 into 23 pixels here. Also, the angles that are expressed in degrees cannot be interpolated. So we now use radians, and then we convert it as numpy cosines, where cosines can be interpolated. So by the formula that is being used, we now have cosine of sun zenith angle. We have the U constant, and we also have the solar irradiance, which is extracted from the metadata. Now we interpolate it with band values, and then we compute it, using which now applying the formula, the radiance is computed. And then let's visualize the task processes in it. So by using radiance.data.visualize method, we see the task graph, and then we can also plot them. Thanks for your time.